The last type of reaction we will take a look at for ketones and aldehydes are the reactions of the alpha hydrogens. So let's define what the alpha means here. I've mentioned previously that we are going to look at the functional group present in the molecule, and the first carbon that is directly attached to the functional group will be the alpha carbon. So in ketones and aldehydes, the functional group is the carbonyl, and the carbonyl contains one carbon. So the carbonyl carbon is part of the functional group. The carbon next to the carbonyl will be the alpha carbon, and the carbon next to the alpha carbon will be the beta carbon. Of course, for this particular case, we have two alpha carbons, one on the left, one on the right. The hydrogens that are attached to the alpha carbon will be called the alpha hydrogens. Alpha hydrogens are relatively reactive for aldehydes and ketones. Alpha hydrogens or alpha proton will be acidic with a pKa of 16 to 20. So if you look at the proton, it's attached to a carbon atom. Typically, we say the hydrogens on carbon are not very acidic. So why is the alpha proton of the carbonyl acidic? Back to chapter 4 regarding the acids and the bases. I said this many times in class. If you are asked to compare the acidity of the acids, you need to take a look at the stability of the conjugate bases. If the base is stabilized, the acid will be more stable, right? So let's take a look at the conjugate base of the alpha hydrogen. If the alpha hydrogen is removed, we will have an anion on the alpha carbon. And because it's on the alpha carbon, it has the CO double bond right next to it. We can draw the resonance structure that the oxygen will help to share the negative charge. Alright, so the ion is actually called the enolate ion. So when the alpha proton is removed, it gives the enolate ion. And the enolate ion is resonance stabilized. That is why the alpha proton is acidic. It's more acidic than other hydrogens on a carbon. We've talked about the keto-enol tautomerization before. In the keto form and the enol form, the difference is the position of one hydrogen, and that is the alpha hydrogen, right? In the keto form, the alpha hydrogen is on the alpha carbon, but in the enol form, this alpha hydrogen moved to the oxygen. The keto form and the enol form are tautomers. Tautomers are actually constitutional isomers. Unlike enolate, the anion, the two forms are resonance. Alright, so let's take a look at some reactions involving alpha hydrogens. The first one is called racemization. If the alpha carbon is a chiral carbon, if the alpha carbon is a chiral center, under either acidic or basic condition, for some time, you will get a racemic mixture, even if you start with one pure enantiomer. How could that happen? So let's take a look at the mechanism for racemization. Let's say under acidic condition, the first step will always be protonation. The carbonyl oxygen will be protonated. Next step, water will take the alpha hydrogen, form the CC double bond, break the CO double bond. So you get the enol form. This is how the enol form is formed under acidic condition. In the enol form, the alpha carbon, it's a double bonding carbon now, it's sp2 hybridized. So it's flat. And we know the enol form is not very stable. It's not as stable as the keto form. So when the enol form goes back to the ketone form, there will be one hydrogen added to the alpha carbon. It's sp2, it's flat now. When that hydrogen is added back to the alpha carbon, it could be added either from the top or from the bottom, giving two enantiomers. Okay, so here is the arrow to show how it goes. The electrons on the OH goes back to form the CO double bond, and the CC double bond breaks. And those electrons will pick up a proton from the solution. The proton could be added either from the top or from the bottom face of that double bond, giving a pair of enantiomers. So that's the racemization on the alpha carbon. And this is the mechanism under acidic condition. If it's under basic condition, then the base hydroxide will grab the alpha proton because that's the acidic proton, and the double bond forms, CC double bond forms, and the CO double bond breaks. Then it gives the enolate. Again, in the enolate, alpha carbon is sp2 hybridized, it's flat. And when the enolate goes back to give the keto form, the proton can be added either from the top or from the bottom, giving a pair of enantiomers. Alright, so this is the mechanism under basic condition for racemization. The second reaction regarding alpha hydrogens is called deuterium exchange. Because alpha hydrogens are acidic, so under acidic or basic conditions, they can be removed and put back. So if we provide the isotope of hydrogen, deuterium, in the solution, deuterium can go to the alpha carbon. For example, here if we do it under acidic condition, instead of having H3O plus hydronium ion, we have D3O plus, the deuterated hydronium ion. Then the alpha hydrogens will be replaced by deuterium. And you need to take a note here, because we are in the deuterium environment. All the alpha hydrogens will be replaced by deuterium. All of them, okay, all alpha hydrogens. So in this particular case, the two alpha hydrogens will be replaced by deuterium. Next example, under basic condition. If we use OD to replace OH hydroxide in D2O instead of H2O, all the possible alpha hydrogens will be replaced by deuterium. In the ketone, we have 2 alpha hydrogens. So in this molecule has 4 alpha hydrogens. All can be replaced by deuterium.